Every time you send an email, buy something online, or just do pretty much anything on the internet, your security is protected by this one single brilliant mathematical trick. So today, we're going to crack that open. We're going to look at RSA encryption, how it works, why it's been the king for so long, and the quantum storm on the horizon that could bring the whole thing crashing down. It really all starts with this fundamental puzzle. You see it right here. How do you send a secret message when you have to assume that someone is always listening in? I mean, to communicate in secret, you first need to agree on a secret code, a key. But how in the world do you share that key over an open channel like the internet without someone else grabbing it first? It seems impossible. Well, this is what cryptographers call the key distribution problem. And for a long, long time, it was kind of the internet's original sin, that first giant hurdle we had to figure out how to get over. And this right here shows you the fatal flaw in the old way of thinking. So let's say Alice wants to send a secret key to Bob. An eavesdropper, we always call her Eve, can just swoop in and intercept it. And that's it. It's game over. Eve now has the key to unlock every single one of their secret messages. This one vulnerability made that old-school, single-key encryption totally unworkable for something as big and open as the internet. But then came the solution, a totally revolutionary idea, public key cryptography. Instead of just one shared secret key, this system, which we also call asymmetric cryptography, uses two different keys, one public and one private. And this changed the entire game, because you suddenly didn't have to share a secret key to get started. And that brings us to the really cool part. The core concept here is this elegant, almost magical idea known as a mathematical trapdoor. Okay, so what on earth is a trapdoor function? Well, just like it says, think of it like a math problem that's super easy to do one way, but incredibly, ridiculously hard to do in reverse. That is, unless you have a secret piece of information, the trapdoor, that suddenly makes going backwards a piece of cake. And this slide just lays out RSA's specific trapdoor perfectly. On the left, you've got the easy part. Take two gigantic prime numbers and multiply them. A computer can do that in a blink. But the hard part, on the right, that's starting with the final product and trying to figure out which two primes you started with. This is a famous problem called the integer factorization problem, and it is the absolute bedrock of RSA's security. And let me tell you, we're talking about massive numbers. For a standard 2048-bit key, the safety of your emails, your banking info, your entire digital life, it all hangs on the fact that trying to factor a number this huge would take even our fastest supercomputers today thousands of years to crack. That difficulty, that is the lock. So that's the math theory, but how do you actually build a real encryption machine out of it? Let's see how this trapdoor gets put to work. The whole system works with a key pair, like you see in this table. First, you've got the public key. You can share this with absolutely anyone. Think of it like an open padlock. Anybody can use it to snap a message shut. But then there's the private key, which comes from those secret prime numbers. You keep that hidden. It is the only key in the entire world that can open that specific padlock. All right, let's just walk through a super simplified example to see how this works in practice. Let's say the message we want to send is just the number 88. So the sender takes the recipient's public key, the one that's available to everyone, and uses it to encrypt the message. And as you can see, our number 88 gets mathematically scrambled into this other number, 121. To anyone listening in, 121 is just meaningless noise. And now for the magic. The person who gets the message uses their secret private key. This is the trapdoor we were talking about. It instantly reverses the math, turning that scrambled number 121 right back into the original message, 88. It works. And the best part is, only the person holding that private key could have possibly unlocked it. But, and this is a huge but, for all its genius, RSA's security is built on one massive assumption, that our current computers just aren't strong enough to find those prime factors. Well, there's a new kind of computer coming, and it's about to completely change the rules of the game. This timeline really puts the threat into perspective. The idea for this kind of crypto actually goes all the way back to 1973, but then, in 1994, a mathematician named Peter Shor published an algorithm for a quantum computer, one that could theoretically smash RSA's lock. And now, decades later, a lot of experts are saying the 2030s, that could be the decade this threat becomes very, very real. And this slide shows you just how big of a deal this is. A classical computer, the one you're using right now, takes thousands of years. But a powerful quantum computer, because of the wild way it computes, it could solve that same problem in a matter of hours. The mathematical trapdoor that protects everything would just vanish. This has led to a pretty scary strategy you hear about in intelligence circles: harvest now, decrypt later. What it means is that adversaries are probably scooping up and storing huge amounts of our encrypted data today, just waiting for the day they can switch on a quantum computer and read all of it like an open book. But the story doesn't end with doom and gloom. This threat has kicked off a massive global race to find a quantum-proof future. We're now entering the next chapter in the history of cryptography. See, researchers are already hard at work on a whole new generation of mathematical trapdoors. It's a field called post-quantum cryptography. And instead of prime numbers, these new systems are based on totally different kinds of hard problems, like finding your way through an incredibly complex, high-dimensional maze, or solving hundreds of equations all at once. These are problems that we think will be hard even for a quantum computer. And that leaves us right here with the big question. For nearly 50 years, the beautiful difficulty of factoring prime numbers has been the guardian of our digital world. The question now is, what new math are we going to trust to secure the next 50? The search is on, and really, the safety of our entire connected world depends on what we find.